Now, welcome back. Now, don't know if you noticed, but this will be your last video of the whole course. You have a couple of assignments and you're almost done. So hopefully you survived and made it okay. So in this video, we're just barely going to touch on fraction operations. I stuck mainly in this course to whole number concepts and understanding. I could actually do a whole course just on fraction understandings, but I won't put you through that, I swear. So in this one, we're going to look at the operation of fractions. So this just is a recap of where the standards fall. And so the last video really focused in on third grade understandings. And now we're going to look on fourth, fifth, and maybe a little of sixth. All right, this is one of my favorite all-time favorite tasks. When I do this class in person, we usually spend anywhere from an hour to an hour and a half on it. It is so fun. I mean, my definition of fun. So I'm going to ask you to attack this problem. And I will tell you right now, in order to make sense of it, you are going to need some sort of visual representation, whether you have blocks, whether you have some drawings. I guarantee if you go straight into, an algorithm or a number sentence, you're not going to get it right. I know some of you are thinking, challenge accepted. You'll see. All right, so the purpose of this task is really to show the importance of not using or having the correct procedural understanding, but about thinking about through the problem. The two glasses of milk being combined, we tend to look at it and go, oh, I just need to pour them in together and find a common denominator and add them up. I'm telling you right now, it's not going to work. So hit pause. Work through this. Don't feel like you have to get to an answer to get to the right answer, okay? But really spend an honest effort trying to work through this. Maybe find a partner to do it with you. When you're ready to move on, hit play, and I'm going to go through some student examples. So how'd you do? These are actually the most common incorrect answers. Did you get one of these? 7/12, 5/6, 5/12. Now, the thing about these incorrect answers is there's some really solid reasoning behind them. They're not just these random things that we got because we miscalculated. There's actually reasoning behind why teachers and students get these answers. So let's look in the next video or next slide and let's see some solutions and possible ways to think about this. Now, I have sequenced these to be progressive in abstract, so more concrete to abstract. All right, so in this example, the first glass has 1/3 cup of syrup, chocolate syrup. So in this very first one, we see that the student has taken, think of these as Unifix blocks, and we have two brown ones representing the chocolate, and then the rest are white representing the white milk, but the whole thing is 6 units. Now, in the second part of the problem, it says the second glass is twice as large as the first one. So in this model, the glass should be twice as large. So there's the first 6 units. Now, why 6? Why do you think? Probably because I could easily take a third. 2 out of the 6 is 1/3. And then I have the second half. So it's 12 units, and a fourth of 12 is 3. All right, so then the problem says now they dump them into a big container, which means all of this gets represented here. And I can now count up my units and have 5 out of the 18. So 5/18 is my correct answer. The problem asks how much of the new mixture is chocolate syrup. So I have 5/18 of the new mixture. So let's look at some additional samples. Okay, this one is very similar. Take a second. Where is the first cup with a third? Where is the second cup that is twice as large? that is a fourth of the total. And then why did this kiddo, instead of stacking up here the twice as big, how did they represent the twice as big? All right, let's look at another one. All right, take a second and think about, what did this kiddo do? Pause and then hit play when you're ready. All right, so let's break down what these thirds and halves and fractions mean. Okay, so let's look at this 1/3 times a third. I have one of my cups is a third chocolate. So I know one of these means a third. I know my other cup is twice as large and it's a fourth chocolate. So I know this is my second cup and I know this is my first mixture. Now let's look at what this means. That means out of my whole mixture, my whole new mixture, a third of that whole new one is going to be this much chocolate. And 2/3 of that whole new mixture is going to be this much chocolate. I keep forgetting to put my laser up. Okay, so how they got the 1/3 and 2/3 is like from the previous model where I had this, and it looked like this. This right here is this third. It's a third of the whole thing. And this is twice as large. It is 2 1/3 sections, which I can see on my diagram. And that has a fourth. And then from there, then the student just starts to add it up. This one really focuses on decomposing a number and flexible thinking. Consider what is happening in each line and why the student is doing what they're doing. What changed from line 1 to line 2? Let's take a look. I have 3 1/3 plus 2 25%. Where did we get those from? What do you think the student is thinking? All right, I'm going to have you get started on this one. Okay, so I'm going to bring back my conceptual drawing from a couple slides ago. We know that this first cup right here is a third chocolate. That is this, it's a third of that piece. Now, where do these 2 25s come in? I know that it said I have 25% of something twice as large. So I'm going to have, let's see, so I'm going to have 25% of this third and 25% of this third. This is still 25 of that whole second cup. That whole second cup right there. So that 25 is that, and that 25 is that. All right, so now let's look at what they did in the second line. They have 3 25s plus 8 1/3. Where did that 8 1/3% come? If I decompose 33 into, I can decompose it into a 25 and with 8 1/3 left over. So now I have my 3 25% with my 8 1/3. All right, so let's go to the next row. I think this kid is trying very, very hard not to actually do any computing. Watch what he does in the next line. I'm going to erase my screen here. We have 8 1/3. I know that I can get 3 sets of 2 out of that 8 1/3. Oops, stupid computer, if you just saw my balloons. Okay, so I can take 6 out of that 8 1/3, and that's how I get this 2 1/3. And I'm going to put 2 here, 2 percentage points here, and 2 percentage points here. Okay, so now I have 27 3 times plus 2 1/3%. Now, if I take that 2 1/3% and I split it into 3 equal groups, I know I can times both of them by 3 and get ninths and get 21 ninths. And 21 ninths is 7/3 3 times. So if I take, I'm sorry, 7 of those ninths and give each one 7 ninths, I now have 27 ninths. Now I have the chocolate distributed between the whole mixture equally, which gives me 27 and 7 ninths. Now, if you want to hit pause and you want to play around with this and you want to keep figuring out what this could do, go for it. So now's a good time if you want to take a mental break. We're going to move on into number strings. We talked about number strings in our whole number computations. Number strings are really fantastic for building fraction computations. So take a look at the first number string. We have 4 1/2 plus 1/2. What is that? 5. 4 1/2 plus 3/4. It's 5 1/4. Now, did I have to find common denominators to do that? No, using the problem string above it, the second one, let me just find my laser. Hopefully you can see that. The second one, so this problem is the same as the above problem, except it's a quarter more. So I know it's going to be 5 1/4, and so on. So these are constructed to help build that number sense and understanding without ever having to find common denominators. If we skip down to the very bottom one, I have 4 1/2 plus 7/12. Well, I know 4 1/2 plus 1/2 is 5, and that's only a 12th more. All right, so take a minute and look at this problem. This is just to get your brain going with the math. And then the next video shows how a teacher facilitates a conversation in an authentic, genuine way with context that allows the students to start using the clock to make connections with time and fractions and really deepening their fractions. So take a minute and just kind of fiddle with this for a second. And when you hit play, the video will start.
Some of you guys know from talking to me about where we live in the city and stuff that I live on the Upper West Side, really close to Central Park. And recently, I decided I needed to start exercising more. So I decided I'd start running in Central Park. They have that big, nice loop. You guys seen the loop in Central Park there? You've been to Central Park, right? And when I decided I was going to start running and talking to people, a lot of people had advice for me about how much I should run, how much I should walk, should I do a combination of both. Alex suggested that I start by running for 1/3 of an hour, and then I walk for 1/4 of an hour. And I was wondering if you guys could tell me how much time that would be. Dylan.
That's 35 minutes, because 1/3 of a mile, 1/3 of an hour is 20 minutes, and 1/4 of an hour is 15 minutes, and 20 plus 15 is 35.
How many of you guys solved that in a similar way to Dylan here? Oh, everybody? Anybody think of it in a different way? Corey?
I kind of did it as like what times the denominator, which was 3 for the first one, would give me 60, because 60 minutes is in an hour.
Okay.
So 20 times 3 gives you 60. So that's how I got 20 minutes. And then 4 times 15 gets you 16 minutes, 60 minutes. And that's how I got 15.
So you thought that 3 times what equals 60? Mm-hmm. And you thought 4 times what equals 60? And that ended up being, for this one, 20 minutes. And for this one, 15 minutes?
Mm-hmm.
And then you put them together to get the 35 minutes again? Anybody think about it any differently? No? What portion of an hour? What part of an hour is that? Lucy, what do you think?
I think that it would be 7/12ths of an hour. It could also be 35/60ths of an hour, but it's easier if you reduce it. So, and I thought of it in 5-minute chunks, and each 5-minute chunk would be a 1/12.
So if you were looking at a clock, and there's our center, and 12 was up here, and 3 was up here, you were looking at 5-minute chunks like this?
Yeah.
And you thought that a 5-minute chunk was 1/12 of an hour? Okay. So when we're looking at the clock, we think of the 6 being here and the 9 being here. And our first fraction was 1/3 of an hour. And you're saying that that was equal to 20 minutes. So that would be right about there from our 12. And then we've got another 1/4 of an hour on top of that. And you said that that's another 15 minutes. So there's another 5, 10, and another 15 minutes. So that goes all the way over to there, which ends up being our 7/12. Is that what you were thinking? Okay. All right. Now, Jess had some different advice for me. She said that I should run for a half an hour, and then I should walk for 2/3 of an hour. So I want you to think about what part of an hour that would be for me here. Just give me a thumbs up when you've got an answer for that. Andres, what do you think about that?
I think it's okay. I think it's for this Scott.
That's all right. Victor, what do you think about that?
I think it's 70 minutes, 1 hour and 10 minutes, because a half an hour equals to 30 minutes, and 2/3 equals to 40 minutes. So an hour, I thought of it as an hour is 60 minutes, and if you take away the 10 from the 40, that would equal 60, and that would be an hour over.
If you take away the 10 from the 40.
Yeah.
It's 30.
From the 40 to make it 30.
Yeah, and you're adding
30. Oh, I see. If you were thinking of the 40 minutes as 30 minutes plus 10 minutes?
Yeah, and then those two, the 30 minutes, the original 30 minutes plus the 30 minutes from 40 equals 1 hour. Then you still have that 10, which is an hour over, so that's an hour and 10 minutes.
So altogether that equals 70 minutes or 1 hour and 10 minutes. Here we had 30 out of 60 minutes, and here we had 40 out of 60 minutes, which altogether gave us 70 out of 60 minutes, or 1 and 10 sixtieths. What if I had 10 sixtieths plus 1/2? What part of an hour is that? Just give me a thumbs up. I'm going to give people a chance to think. Veronica, what do you think about that?
I think it's 40 minutes because 10 60th is 10 minutes out of 60 minutes, and 1/2 of an hour is 30 minutes, so 10 minutes plus 30 minutes is 40 minutes.
So you were thinking of this as 10 60th, and this has 30 out of 60?
Mm-hmm.
And you added those together to get 40 out of 60?
Yeah.
If we looked at that on a clock, starting up here at 12, our first part was 10 minutes, about there. And then we're adding on to that half an hour, half of the clock, all the way over to here, which would be 10, there's our half hour right there, which would be a total of 40 out of the 60. Did anybody else think of that in a different way? Chloe.
Well, I knew that the 10 sixtieths was equal to 10 minutes, and I knew that the half was 30 minutes, so I thought of the 30 as 3 sixtieths, and then I added 3 sixtieths plus 10 sixtieths, and I got 40 sixtieths.
So you thought of this as actually 3 sixtieths?
Yeah.
And you added, tell me the rest again?
And then I added 10 sixtieths plus 3 sixtieths.
And got 13 sixtieths?
I got 40. Because the 10/60ths was like, it was like 1/60th.
How's the 10/60ths like 1/60?
Well, for each, that 10/60ths is equal to 10 minutes.
Okay.
And
So
so,
is 10 minutes 1/60th of an hour?
yeah.
What do you guys think?
No, 10 minutes is 1/6 of an hour.
10 minutes is 1/6
Yeah.
of an hour? So you were thinking about this as 1/6?
Yeah.
Okay.
And then I thought of the half an hour, I guess, is 3/6.
Oh, not 3/60th, but actually 3/6, and put that together and got
4/60ths.
4/6.
Yeah, and then I made it bigger. I made a bigger equivalent fraction to get to 40/60ths.
Okay, and if we look at this, we can again think of that as being 1 to the 6th, this as being a second 6, because each 6 is 10
Yeah.
minutes here. 1, 2, 3, 4, 6 ends us up at 40 minutes. Yeah? Any other ways of thinking about that? I need to erase a little bit. What about if I wanted to run for a third of an hour, walk for 25/60ths of an hour, then I get my second wind. I want to run for another fourth of an hour. How much time am I going to spend out there if I do all that? Take a minute to think about it. Just give me a thumbs up. You've got an answer. Jeff, what do you think about that?
I think that you ran for 60 minutes or one hour, because a third of an hour is 20 minutes and 25/60th of an hour is 25 minutes and a fourth of an hour is 15 minutes. So I added 25 plus 15, which equaled 40, and I added the 20, which equaled 60 minutes altogether.
So you thought of them as all as minutes out of 60 minutes, minutes
Yeah.
out of an hour, 20 out of 60, 25 out of 60, 15 out of 60 all together gave you
60 minutes.
60 out of 60?
Yeah, or one whole.
How many of you thought about it like that? I'm curious. Okay, anybody think about it any differently? No? So what if I was going to run for a sixth of an hour and then walk for a half of an hour? What part of an hour would I be out there for now? Kevin, what do you think?
I would. It's 40 minutes because 1/6 is 10 minutes, and 1.5 is 30 minutes.
So you were thinking of these as 10 out of 60, again, minutes out of an hour, and 30 out of 60. Adding those together, giving you the 40 out of 60. Is there another way to think about this? Other than the 10 minutes out of the 60 minutes, always putting it into 60 minutes, can we think of it in another way?
You could make the half into 3/6, so the denominators would be the same, but you wouldn't have to change both fractions.
Oh, I see. So you were leaving this as 1/6 and thinking of this as 3/6 and going back into 4/6 as your answer, which equals 40 out of 60. Okay. Earlier, Chloe had said something about 7/12 of an hour. Could we think about it along those lines with 12ths? Could we think of it in 12ths here at all? Josephine, what do you think?
Well, 1/6 of an hour equals 10 minutes, but you could find an equivalent fraction, which would be 2/12.
So you're thinking of the 1/6 as 2/12?
Yeah, and then the 1/2 is 30 minutes, which 5 fits into 6 times, so it could be 6/12.
You're thinking this is 6/12?
And then you add that together, and it could be 8/12.
Which altogether gives you 8/12. Where do these 12ths show up on the clock? Can we talk a little bit about that? I always see these 12ths on the clock. Susie, what do you think?
Well,
like there's 12 spaces which are equal to 5 minutes on the clock.
Looking at the numbers here.
Right. So between those numbers, the spaces. Each one equals 5 minutes, and 12, and then there's 60 minutes total, and so 5 goes into 60 12 times, so each one is 1/12.
So every 5 minutes is equal to 1/12 of an hour?
Yeah.
And you're saying that we can see all of these 12 5-minute chunks in our clock there? And each one of those is 1/12 of an hour, or we could even say the 5 minutes there in between. How many of you feel like you understand what Susie's talking about? Yeah? Okay, could somebody else put that into their words? What Susie was saying about the 12ths here? Corey.
Well, like, you know how there are different parts on the clock, like there's 1, 2, 3, etc., all the way up to 12. Well, each number that's on the clock stands as 5 minutes or a 12.
Could you take 30 seconds and just turn to the person next to you and quietly explain that to each other? How many of you feel pretty comfortable with these 10-minute chunks and 5-minute chunks and all the stuff we talked about here? Yeah? So I want to ask you guys, what makes these fractions make sense to deal with a clock? How does the clock model help us deal with these kinds of fractions that we were? Alexia, you want to start us off?
It deals with the clock because you're running for 60 minutes and you're seeing how much time it will take to run or to walk or to jog out of 60 minutes. So basically, that's it.
Well, I think that you start out with minutes out of an hour, and then when the denominator becomes 12, it also makes sense that there are 12 spaces on the clock. So each one that makes up the whole number on the numerator can equal 1 space on the clock.
So since we're dealing with 40 60ths, 60 is 1 hour, and so to equivalent fraction would be 8/12, and since we put it into 12s, we're dividing the 60 into 12s, the 6 hours into 12, and each 1/12 is 5 minutes, as Susie said, and since we're dealing with 8/12s, it equals to 40 minutes.
So we've got these nice chunks of these 5 minutes. We can see the 60ths because there's 60 minutes an hour, but you're also saying there's the 12 chunks of 5 minutes, which helps us see some equivalent fractions too. Like 8 of those 12ths would be... Colin, somebody else get some other thoughts.
Lucy? I also think it's helpful to use a clock because 12 and 60, I think they're really good denominators to have. 2 goes into it, and a lot of numbers that are also common denominators that you see a lot in denominators can go into 12.
So both the 60 and the 12 are numbers that you can split up into other chunks. Is that what you're saying?
Yeah, but you can split them up. Like a lot of numbers go into them. They have a lot of factors.
A lot of factors. Going back to front. Okay. You have to kind of turn around and see other people.
Josephine?
Well, it's easy to see on the clock the fractions because it's sort of like a whole portion, and then you can see the clock broken up into the 12ths and the 60ths and the 6ths.
So you're saying that these 12ths are easy to see on the clock and these 60ths are easy to see on the clock. Can we think about the fractions that would make sense to work with a clock if we know that a clock is 60 minutes and we've got all this other stuff we've talked about? Josephine.
Like, third.
So you're saying that a third works. Other thoughts here? Jeremy?
Half would work easily.
1/2, 1/4. Other ones? Victor.
1/6.
1/6.
And 1/12.
What I hear?
1/12.
1/12. Any other ones you think make sense to work with a clock model?
1/60th.
1/60th. So 60ths. What else?
I'm not sure, but maybe 1/20ths.
20ths? Why do you think 20ths might make sense?
I mean 1/20ths.
120ths.
Yeah.
Oh, like 1/20th?
Yeah.
Like that? Why would you think that? Why would you say that?
I think because that's half of the 60th, and I think that if you had something with that denominator, you'd just know that one of those would be 30 seconds because 1/60th is a minute.
So you're saying that 1/60th equals 1 minute. So 1/20th equals 30 seconds, or half of a minute. So you think that 1/20th would be easy? Okay. Well, until we got to here, what do you notice about all these? What makes these, can we sort of name what makes these things, makes these fractions that work with a clock model, that help us to think about with a clock model? Jeremy, what do you think?
I think they're all equivalent to each other and to 60.
So a third is equivalent to a half, is equivalent to a fourth?
No, like, well, no.
Other thoughts on this? What do you think?
Susan?
Any new voices over there? Go ahead, Susan.
I think that all of the denominators are either factors or multiples of 60.
Oh, so 3 is a factor of 60, 2 is a factor of 60, 4 is a factor of 66, 120 is a multiple of 60, factor of 60. 60 a factor or multiple of 60?
Yes.
Which one? Both. All right. So what I'm hearing you guys saying is that as far as a clock model is concerned, these fractions all make sense to work with clock models, help us think about adding the fractions, because all of their denominators are either factors of 60, and they're 60 minutes an hour, or even multiples of 60. So we can think of them as chunks of 60 minutes really easily, and the clock model helps us to add these fractions together. So since we're thinking of
Numberless word problems are a way to teach explicitly to students while making sure everyone is still on the same page as you move forward. They present an opportunity to model metacognitive thinking in class. So here's one. What question do you think we're going to ask? Jill and Maria decide to go for a hike. They start early in the morning and hike so many miles before stopping for lunch. After lunch, they hike some more miles. When they finish their hike, they had walked a bunch of miles. Now, what question do you think I'm going to ask? What do you think is under the orange bar? What do you think is under the gray bar? All right, so here's my question. How many miles did Jill and Maria walk after lunch? So I might encourage you to draw a number line right now and draw out this story with no numbers. What would be a reasonable total? So did you put your values on a number line? Okay, so you had it drawn and now we've got some values. What range could we expect to be our final answer? All right, I took off the orange bar and now it says 5 3/4 miles. How does this change your number line? How does this shift things? What is the possible range of what we could have? Take a moment to look through each of these problems. For each, think about how having a deep understanding of how to model and name fractions would enable students to solve these problems conceptually before ever being introduced to algorithms. For the two addition problems, we can think about that idea of identifying the size of the piece. In this case, both fractions are already in fifths, so we can simply count the total number of fifths we have, 7/5 or 1 whole, and 2 more fifths. In the second problem, we have different sizes of pieces, fifths and halves. In order to add them, we need to partition both to get equally sized pieces. We can partition both into tenths so that we are adding 6/10 and 5/10 to get 11/10, or 1 and 1/10. Through these kinds of experiences, we are building towards the concept of common denominators and common multiples. This is a really fun task that that low floor, high ceiling, and it really requires some visual representation. So click pause and start to solve this problem. Hit play when you're ready to continue. Take a minute to look through these 6 problems. For each, think about how having a deep understanding of how to model and name fractions would enable students to solve these problems conceptually before being introduced to standard algorithms. Draw a model to show your strategy for solving each of these problems. For the first multiplication problem, we see an application of unit iteration and partitioning. 2 times 2/3 is 4/3. And then another half of 2/3 would be an additional 1/3 to get 5/3, or 1 and 2/3. In this problem, we see partitioning. In problem D, we see partitioning. To find a fourth of the whole, we partition into 4 equal pieces. To find a third of that fourth, we partition into 3 to make 1/12 pieces. But because we want 2/3 of 1/4, rather than just 1/3, we take 2 of those 1/12 pieces to get 2/12. We can see them as 1/6, as it would take a total of 6 of those to fill in the whole area. In this second problem in particular, we can start to see connections to the fraction multiplication algorithm of multiplying numerators and denominators. So this idea was covered in the Ralph's Garden problem, but let's take a second to draw an area model for each of these problems in this number string. I'm going to get you started. So if I have my rectangle and I split it into fourths, okay, here's my fourth. And then I need a third of that fourth. So there's my fourth. I'm going to take a third of it. Now, I don't normally stop right after that 1/4. I'm going to actually extend this out because I need to know how many are in that whole shape. So now I know I have 12 pieces, and a third, writing with my finger here is not working. So a third of that 1/4 is 1/12. So take a second and draw out area models for the rest of these problems and start to connect on why this is working. See if you can think about that. What strategy might you use to figure this out? What model best represents that strategy? Take a minute and see if you can do an area model. Maybe there's a ratio table. Maybe there's something else. See how, without knowing an algorithm, how could you figure this out? Let's take a second and figure out what these students did. Let's look at student 1. They used a ratio table. So I need 2 and 2/3 times 6 1/2. So I need what? 6 1/2, 2 and 2/3 times. So here in my ratio, 1 is 6 1/2. I need 2 and 2/3. So 2 of those 6 1/2s would be 13. Now I need 2/3 of each. I need 2/3 of 6 and 2/3 of a half. So 2/3 of 6 is 4. 2/3 of a half is a third. Now I had to hit pause for a second because I made myself think, is 2/3 of a half a third? Well, I didn't even finish the calculation because I went, oh, the commutative property. If I have half, what's half of 2/3? It's the same thing, it's a third. So it is 2/3. Now all I have to do is look at, I need 2 and 2/3 of 6 1/2, which is putting those two pieces together. Pretty interesting, right? All right, let's look at student 2 and see what they did. All right, so I have 2 and 2/3 times 6 1/2. So this looks pretty traditional to me, right? I have 8/3 in my 2.5, or 2 2/3, and then I have 13 halves. I put all those together and then I simplify or reduce. Now, I love student threes. They used an area model. So we still decompose. There across the top, I have my 6.5. Down the side, I have my 2 2/3. And then I multiply. So 2 times 6 is 12. 1 times a half, or half of 2 is 1. 2/3 of 6 is 4. And 2/3 of a half, or I switch it around, half of 2/3 is a third, or 1/6, or 2/6. And then I put all those together. So earlier I had you take a look at these problems. Right now we're going to look a little more deeply into the bottom two. The numbering on these is a little off, I apologize, but it's the two division ones. So in division, we can go back to measurement and part of the division context to help us. We might think of 3 divided by 1/4 as asking how many 1/4 size pieces are there in 3? Because each one whole contains 4/4. We know we have 12, a total of 12/4. Now, looking at the problem F on this screen, we have 3/4 divided by 3. Can be looked at from a partitive division lens. So basically, if we have 3/4, we know that's 3 1/4 pieces. So that means we need groups of 3. We're going to have a fourth in each group. We're starting to see the connections to an algorithm of multiplying by the reciprocal. This is why this is starting to work. So this number string was one of my absolute favorite number strings to do anytime I walked into a 5th or 6th grade, 7th grade classroom. And usually I could use this one in 7th, 8th, or 9th grade because student fraction understanding is still really, really fragile. And I love this number string because it posed such amazing opportunity for really good discussion. It surfaces students' misconceptions. So without ever having to have an algorithm, without having to learn about the flip and multiply or invert and multiply, let's just kind of walk through this a little bit. So what is 4 divided by 2? How many groups of 2? Now notice my language. How many groups of 2 are there in 4? We know there's 2. Well, how many whole groups are there in 4? Well, now we know there's 4. Well, if I had half pieces, how many halves are in 4? So at this point, kids can start telling me that what they're visualizing, right? So I can draw 4 and I can count up how many halves are in that 4. So I know there's 8, and already they're starting to see this pattern of doubling. So my number's getting cut in half, and I'm seeing this pattern, but then I switch it on them. And I say, oh, well, if I took my 4 pieces and I cut them into thirds instead of halves, how many would that be? Well, they're starting to figure out, oh, mentally, I can switch this to 3. So now I have 3, 6, 12. 3, 6, 8, 12. Can't count. Okay. Now, if I take those third pieces and I glue them together, and I call this a chunk, this 2/3 chunk. I have 2 1/3 pieces. How many of those two 1/3 pieces would I have together? Now, visually, you can see that they're starting to, let me get a different color. They'll start to take their whole that's divided into thirds, and sometimes I'll draw these on the boards as they describe them, and they're visualizing gluing some together like this. Okay, and if I see if I can get rid of these. Yeah. Okay. And I have this, and depending on the age of the kids, we have to deal with leftover pieces. So sometimes they'll say, oh, well, I have 4. And then kids will go, but that doesn't follow our kind of our pattern because we know this is 12. So is this going to be 6 or is it going to be 24, right? Well, I have 1, 2, let me get my laser, 3, 4. But then we point out, usually one of our kiddos does it, go, well, you have to glue those two together and you have to glue those two together. So now I have 6. So now I ask, okay, well, what if I had 5 holes? Now what this does is this changes this to look like this. And they've got the 6 plus the 1 more. So they know they have 7. Now, I always, 100% of the time, I'm going to ask you, what is the correct answer? Do not go use the algorithm. 100% of the time, we have this discussion. The answer is either 7.5 or it's 7.33. Which is it? Is the answer 7.5 or the answer 7.33? And why? Now, this is a really important conversation. And if you're struggling to really prove it and you have to go invert and multiply to prove it, that shows that your own understanding is not as secure as we would want it to be. So is the answer 7.5 or 7.33? Well, let's debate this. This piece is a third. So kids are convinced, adults are convinced the answer is 7.33. However, what is my new whole? My new whole that everything is being designed around is this 2/3 chunk. So there's a 2/3, there's a 2/3, this is a 2/3. Well, this 1/3 piece is half of my 2/3. So what is my whole? My original whole was the whole size, but my new chunk that I'm trying to find is the 2/3. So my answer is actually 7.5. Now, if you're sitting there and you're going, yeah, I told you so, I knew that. I want you to think about how you knew that. Did you know it because you inverted and multiplied, so you know the 2 was going to be on the bottom? Or could you justify it conceptually? And those of you that are sitting there with your minds blown, go back and rewatch this and draw it and make sense of it. So a problem like this can be used to show that when we have common denominators, we divide the numerators. The twelfths become the units and we're grouping by parts. So draw a picture to solve this task. Rhonda likes the cake, so she decides that a serving is going to be 1/12 of the cake. So how many servings can she make from 7/12 of the cake? All right, see if you can solve this one by drawing out a number line. Draw your 11/35 and divide it by 3. With no context, I don't know how many's in a group, or I don't have to know, or it doesn't tell me how many's in a group or how many groups I have. So you can decide. Now, I want you to do it with a number line so that you can see something very clearly. Hit play when you're ready. Okay, how did that go? You should have something that looks like this. You've got your number line, and I'm not going to draw the 11/35. I'm certainly not drawing the 35th. That's one of the beauties of this one. But I can circle for every 3/35, I can circle. So there's going to be 3/35, 6/35, 9/35, and then I'm going to have 2/35 left over, which is 2/3 of that whole. So my answer would be 3 2/3 35ths. All right, so this is the last problem of the day, of the module, of the course. Yay! Okay, so Lucy has 5 gallons of fruit punch for the party. She has a number of pitchers that will each hold 2/3 of a gallon of punch. How many pitchers can she fill? How much punch will be left? Using the pitchers as a unit, describe the amount of capacity she will use if she puts all of the punch into pitchers. Hit play when you're finished. Okay, so this is one way that you could have drawn out a solution where you draw the 5 pitchers and you have 2/3 being poured into each one, and then we keep going, and then we have that leftover piece. So the purpose of this type of problem is to really address what I brought up in that number string problem is, what do we call those remainders? How do we name those? That is a crucial understanding when we talk about naming them. Is it a third? Is it a half? So this is really an important part of our understanding. So we're going to have 7 and we're going to have 1/3 left over. So fraction relationships and operations can really be an opportunity for deep mathematical thinking and reasoning and problem solving. That's what we've been trying to build this whole course. But we have to look beyond getting an answer or computing and getting an answer. We have to provide the kids with these opportunities to explore, to reason, to figure out, and to make sense of the parts and pieces. Okay, we have to help them to develop that reasoning. This really supports their learning of algebra and advanced mathematical concepts. I could teach an entire course just on fraction operations. I could build one. I might do it. I don't know. I'm a little tired now. But the main idea from this section that I want you to walk away with more than anything is that all of the whole number operation information, all of it, applies to fractions, decomposing, skip counting, modeling, strategies. All of those strategies and models are the same. We need to help kids by spending time exploring and making sense. So that's my goal for this module. Now, you've finished this up, so you've got a few more assignments to do and you're almost done.